This video is about reaction mechanisms, and I strongly recommend you read the chapter notes on pages 383 to 391 in your textbook. So we'll start by saying consider the reaction of 2 octane molecules and 25 oxygen molecules reacting to form 16 carbon dioxide and 18 water. It is statistically unlikely that the reaction occurs by the simultaneous collision of 27 reactant molecules. So when we write out this reaction, effectively what we're saying is that 2 octane molecules will collide at exactly the same time with the correct amount of activation energy and the correct orientation with 25 oxygen molecules. That is statistically unlikely to happen. The probability of 27 molecules colliding at the exact same time with the correct energy, with the correct orientation, is unlikely. This made chemists think that overall chemical reactions, so like this overall chemical reactions, are actually occurring in smaller steps. So chemical reactions occur by a series of one or more simple steps involving particle collisions. Called elementary steps. To recap, the overall chemical reaction, as written above, does not happen in one step. It's made up of multiple steps that altogether make up the overall chemical reaction. So we have what's called a reaction mechanism, which is a series of these elementary steps that make up a chemical reaction. So this reaction mechanism is most often theoretical. It is what chemists think is happening to produce the overall reaction, supported by some evidence, as we'll see later. So this right here is an example reaction mechanism. So right here we have an example reaction mechanism. In this reaction mechanism, we have 3 elementary steps. So these right here are my elementary steps. So I'll just draw that on so you guys can see that. Elementary steps. Okay, these 3. You have a slow step, a fast step, and a fast step. And so the slow step, this is the slowest step of the entire reaction mechanism. This is what we would call the RDS, or the rate determining step. So this being the slowest step in this reaction mechanism that produces an overall reaction, this one being the slowest here is going to control how fast the reaction goes. So it is the rate determining step because it is the slowest step in the entire mechanism. It controls the rate of the reaction. So it controls the rate of the reaction because if it's the slow step, then the rest of the reaction can't happen until this step happens first, right? or until this step is completed. So the reaction can only go as fast as this step. If we were to take a look at the overall reaction here is going to be 2x plus y goes to form C. So the reaction intermediates in this reaction mechanisms are substances first generated and then later consumed during the reaction. So if we take a look at that, I'll highlight them in green. We generate Z right there. Then Z produces A and B. Then 2A and B are then consumed to form C. Now just to quickly just fix one thing here, it should be 2x plus 2y, since there are 2 y's present. Okay, and we see that Z cancels here, the A's cancel, the B's cancel, and so the overall reaction is 2x plus 2y goes to form C, where the reaction intermediates, the substances that are produced and then consumed, are Z, A, and B. A rate law is a mathematical expression that shows how the rate of a reaction relates to the concentrations of the reactants. So how much does the concentration of a given reactant affect the overall rate of reaction? And rate laws could be written for any of these elementary processes. So given an elementary step where you have, little m times big M, so the stoichiometric coefficient little m, big M plus nn goes to form pp, where m, n, and p are our stoichiometric coefficients within the elementary step. The rate law could be written as follows. R, the rate, is equal to K, capital M, raised to its stoichiometric coefficient, concentration of N raised to its stoichiometric coefficient. Okay, where M and N are the stoichiometric coefficients. And M and N are the concentration of reactants in that elementary step. So, as we saw, the rate determining step is the slowest step in a reaction mechanism. So the slowest step in a reaction mechanism. And the rate law for the rate determining step must be then the rate law for the overall reaction. Okay, so because the rate determining step is the slowest step in the reaction mechanism, it controls the speed of the reaction. and therefore the rate law for the rate determining step is the rate law for the overall reaction. So if we looked at the rate determining step in the above mechanism, let's go back to the above mechanism here, was 2x plus y goes to form z. Okay, 2x plus y goes to form z. That was the slowest step in the reaction mechanism. Because that was an elementary step, I can write a rate law for that elementary step. So I would write R is equal to K, okay, which is like a constant of proportionality. Concentration of X raised to the power of 2, concentration of Y raised to the power of 1, and this right here is actually now the rate law for the overall reaction because it's the rate law for the slowest step in the process. Reaction mechanisms are always theoretical. They are proposed but not known. For a proposed mechanism to have any validity, its predicted rate law must agree with rate law obtained from experiments. So in the next section, or in the next lesson, we're going to look at data from experiments, get rate laws from that data, and then from there be able to propose a reaction mechanism or a rate law for the reaction mechanism. Moving on to free radicals. Free radicals are basically an unbound atom or molecular fragment. Okay, so what I mean by that is an unbound atom is effectively like, for example, if we have chlorine. So not molecular chlorine, but just atomic chlorine looks like this, right? And this would be a free radical because it has one unpaired electron, so it is seeking to bond with another atom by sharing an outer shell electron to complete its outer shell. So these are very unstable species because they have effectively an unbound or an unpaired electron that needs pairing, right? When I say molecular fragment, we can also have something like this, like CH3, and you could have basically an electron here, which means that, as you can see, carbon hasn't fulfilled its bonding capacity, and so it still has one electron that it needs to pair up with something. So that would be like a molecular fragment that is a free radical. We use the notation, instead of drawing all the various lone pairs, we usually just do this. We do one dot, and the conversely, if we look at the ion has a complete outer shell. We do Cl with the charge, right? But for the free radical, it's Cl with the dot there, meaning an unbound electron. So free radicals are involved in many reaction mechanisms. Okay, radicals are formed by breaking a covalent bond. So when we break that covalent bond, it is no longer stable because it doesn't have an outer shell. So I just want to put right here that free radicals are unstable species because they do not have a full outer shell. So an example of a free radical forming here is chlorine when exposed to certain photons. If the photons or the packets of light have enough energy, they can break the covalent bond apart and form two chlorine free radicals. So elements that are normally diatomic, shown as single atoms, must have unpaired electrons and be radicals, right? So that this is what creates the free radical. Okay. In order for this to happen, you have to have a lot of energy. So a lot of energy, or basically what we're looking at, a high activation energy, is required to break the bond and form the radical. As such, the free radical has a lot of potential energy. Since a lot of energy was put in to form it, it has a lot of potential energy, so that makes it very unstable, and its instability makes it extremely reactive in subsequent steps. So elementary steps forming free radicals tend to be slow because they have a very high activation energy, whereas elementary steps reacting free radicals tend to be fast. Okay, and because free radicals are so reactive, when those free radicals react, those steps have very little activation energy, because it just allows the radical to react quite quickly. But if we want to make a free radical, when we want to break that covalent bond, that requires a lot of energy, so that's a slow step. So free radicals are often involved with chain reaction mechanisms. So the reason why they're chain reaction mechanisms, so if we take a look at this, right, reaction in the production of HCl, Cl2 exposed to light will form 2 chlorine free radicals. So this would probably be your slow step, right? Because that's forming a free radical. It's got high activation energy, right? These right here will be fast because it involves the reaction of a free radical, right? Even though another free radical is produced, you're still reacting a free radical. This right here will also be quite fast because you're taking 2 free radicals to form a molecular compound, or a molecular element rather, and then same thing here as well. That's going to be a fast step, right? And so your overall reaction in this reaction mechanism shows that you get H2 plus Cl2 forms 2HCl. Okay, so in that overall reaction, this is what happens. Okay. Reaction with CFCs in the ozone layer. CFCs are called chlorofluorocarbons, and those are things that are in refrigerants. So they used to be in air conditioners and in refrigerators, and they also in aerosol cans, and they escape to the ozone layer. And these CFCs, as you can see right here, they would react with light and they would produce chlorine free radicals. And the chlorine free radicals would then react with ozone in the atmosphere, and it would, because it reacts with ozone in the atmosphere, it depletes the ozone in the atmosphere, and in depleting ozone in the atmosphere, the ozone becomes thinner and allows more UV radiation to penetrate. So a lot of the CFCs, the use of CFCs now have been banned. So a chain initiating step is effectively a reaction or step that forms a free radical, whereas a chain propagating step are steps that continue the reaction mechanism. And a chain terminating step is a step where radicals are reacted and the chain reaction ends. So if we were to take a look at this, this one would be chain initiating. These over here would be chain propagating. These would be chain propagating steps, and these ones right here would be chain terminating steps. Okay, we'll end this lesson by looking at catalysts. Catalysts speed up reactions by providing an alternative reaction mechanism. So reaction mechanism with a lowered activation energy. Okay. Catalysts are specific to a particular reaction and are not permanently changed. And there are two types of catalysts. A homogeneous catalyst, which is in the same phase as the reaction mixture. So in the same phase as the reaction mixture. So like in a liquid or gas. A catalyst, basically it participates in the reaction mechanism. First getting consumed in one step and then later regenerated in a subsequent step. So an acid catalyst used for decomposition. So as you can see here, the reaction or the catalyst, the acid, is being consumed in the first step right here. Consumed in the first step, and then in the last step it is reproduced, right? So the overall reaction still involves this. Okay. The overall reaction does not involve H+. We put H+ above the arrow to indicate that it's a catalyst, but as you can see here, it gets consumed initially but then gets reproduced. So that's a homogeneous catalyst. A heterogeneous catalyst, however, is in a different phase than the reaction mixture. Like, for example, finely divided solid catalyst for liquid or gaseous reaction systems. It is a catalyst that provides a surface that adsorbs, not absorbs, but adsorbs, attracts reactant molecules, which may allow meeting at the correct orientation or facilitating collisions with lower activation energy. And an example of that would be catalytic converters in cars that use powdered metal to catalyze oxidation of unburned fuel and carbon monoxide. Okay, so in this lesson we first started looking at reaction mechanisms, which were theoretical mechanisms that break down an overall reaction into smaller steps. We looked at what a rate determining step was and how it controls the overall speed of the reaction. We looked at writing a rate law, so the rate of the reaction is, as we can see here, directly proportional to the concentration of the species in the rate determining step raised to their stoichiometric coefficients. We talked about free radicals being unstable species that do not have a full outer shell, and they are involved in reaction mechanisms because they first form and then they propagate by reacting with other compounds, and then in the end they terminate by finally reacting and being consumed. And then finally, we just looked at catalysts, the two different types of catalysts, both homogeneous and heterogeneous catalysts. Thanks for watching.